All right, cool. Hi everyone. My name is Ian Chen. I'm from Open Robotics, and today I'm going to talk to you about another NASA Ames project. It's one that we collaborated with NASA Ames. Is about the simulation of the moon in Gazebo. Uh, what more specifically is about the simulation of a rover on the moon. This is a simulation environment created for the Resource Prospective Project NASA. So um, the goal there was to send a rover to the polar regions of the moon and to find evidence of volatiles such as hydrogen, oxygen, and water. So NASA's Johnson Space Center was responsible for hardware, and the group we worked with, the NASA Ames, they were responsible for software. And that's the team we collaborated with to create a simulation environment. So in the image you see on the right there, that's a prototype RQ-1A. It's built on top of the KREX mobile platform. It's got active suspension. Each wheel can be controlled individually, and it's got hazard cameras all around the mobile platform and looking at its wheels in case it gets stuck. There's also another camera looking out the back. And on top of the rover, there's a mast that carries a stereo camera pair mounted on a Pentel platform, so you can look around while the rover is being driven. So for this project, we created a simulation environment to assist driving operations. So the robot itself is not autonomous. It's being driven by remote operators on the ground. So our goal is to create an end-to-end simulation environment. We use ROS and Gazebo. So ROS is used to emulate the flight software and ground software. So whether or not ROS, specifically ROS 2 would be used in the actual system was still a topic of discussion back then. On the Gazebo side of things, so the simulated vehicle is the one you're seeing on the bottom right. So it's a simplified version of the actual rover, but scaled to fit the dimensions and mass of the actual rover. It's also only using passive suspension as opposed to active, and that was fine for the driving experience that we were doing at the time. So since we are simulating the moon, let's take a look at what it looks like. So this is a video footage from Apollo 16 mission. It's a mission where they landed at the lunar highlands of the moon. So there are two types of regions, the lunar highlands and the lunar Maria. So here in the lunar highlands, you can see the surface is actually brighter in color. It's got more craters, and it's also the mountainous regions of the moon as opposed to Maria, which is darker region filled with solidified lava. So what you see here is somewhat similar, but not exactly the same as the target site that we wanted to simulate. So at the poles where the rover will be deployed is also in the lunar highlands, but there's some differences here. So what you see in this mission, they landed close to fresh craters, so there are actually more rocks in the scene. And compared to the poles, the sun is also a bit higher in the sky, so you don't see it here. But these are two small important differences that we eventually had to capture in simulation. Oops. Okay. So compared to the projects that we've done in the past, this particular project, we focus a bit on visual simulation. So we also did other things like modeling the vehicle dynamics, but for in this presentation, I'll focus on the environment. The images produced by simulation are important in this project. They want it to be as realistic as possible because that's what the operators rely on when they control the robots and move them around. So we end up with something that you see on the left there. There's an image produced by Gazebo. And for comparison, we have an image from a different mission from Apollo 12. So I think in general, we are satisfied with the results. There are always things that we can improve on and tweak even more time. But throughout this presentation, we'll show you how we created the scene that you see on the left there. So early on in the project, we were given a very high-resolution terrain file. So in the form of digital elevation maps is a format that's already supported by Gazebo. So what the engineers and scientists and NASA did was that they took the actual lunar DEM file and then artificially increase this resolution, and then they inserted rocks and craters to make it as close as possible to the actual site that we're simulating. So we have this really high resolution DEM file. It's roughly 4 centimeter resolution, so that is adequate to simulate the obstacles that you find on the surface of the moon. And then we did rocks and the tiny little craters. So with this high resolution DEM file, when we tried to load it in Gazebo the first time, it took over 5 minutes to load. And then once it was loaded, the frame rate was really bad, especially when we tried to run it on low-end laptops. It was basically unusable. So we know that at the beginning of the simulation, we want to, the project, we want to improve performance, especially related to rendering height maps in Gazebo. So we did 3 things. The first thing is that we added the ability to cache terrain tiles. So we found that a lot of time is spent on loading on Gazebo startup, loading a DEM file, was on just parsing the DEM file and creating the internal terrain tiles format that we use in the underlying rendering engine, Ogre. So assuming the themes don't change, the textures don't change, we could just reuse the same tiles. We don't have to regenerate them again. So in subsequent, what we only have to do is once, in subsequent loads, we were able to get down the time from 5 minutes to roughly 30 seconds. So it was a nice improvement by a factor of 10. And so the next thing we did was that we enabled level details. And it's just best described by the picture on the top right. So the low frame rate was attributed by the number of vertices and triangles that you see. When we zoom all the way out, we see the entire terrain. Basically, there's 2 main triangles, and then we can render them all. So we enable level details. So it's a quad-tree implementation of the terrain. Basically, the nodes can transition to a lower level based on camera distance, and so also the height characteristics of the node in the tree. So as you see in the animation, when you zoom out, we have reduced number of triangles, and then we were able to render it properly around 40-50 frames per second. And the last thing that we did was that we decided that for any of the terrain that the rover isn't being driven on, we don't need high resolution terrain. So anything else, so you see on the bottom picture there, so the bottom right, we use high resolution DEM, and everything outside of it, we just use coarse meshes. So these are collada meshes. And then we build 6 layers out, all the way out to the horizon. So with all these changes, we were able to load the entire terrain in Gazebo. The next thing that we did was we focused on creating the lunar appearance. So the default shading model in Gazebo just wasn't sufficient for the purpose of this project. So they want to use something what's known as the Hapkey model. So it's designed to capture the unique reflective properties of the lunar surface. It's covered by regolith, which is powdery dust and loose rocks that you find over the moon, the surface of the moon. So to do that, what we did is we just worked with them to integrate their own custom shaders to Gazebo. I want to note that we've seen this, people doing this in the community already. People create ocean waves for maritime robotics applications with their own shaders. Maybe you see in the talks and this conference, but that was pretty cool. So for this project, we helped them integrate shaders specifically for height maps, and that wasn't possible before. So now it's available in Gazebo 7 and above. So just a little bit more details about the components inside of the shaders for those interested. So using the same software that they did to generate the high-risk terrain, they were also able to generate various maps. So on the top level there, you have the normal maps, and which gives it nice detail and even look and feel of the surface. You also have the pre-render shadows. We assume that the sun's position relative to the moon stays relatively fixed over the duration of each simulation session. So we can use static shadows for the terrain, but they also will be able to access the real-time shadows that we set up. I'll touch on this topic a bit later, but these are the shadows associated with the rover. And then you have the standard albedo, diffuse maps, and rock masks. For the albedo maps, you can see that the lighter colors are fresh craters, and you can see the splash rays from the impact. And they can also apply their own shading model, the Hepke model, to produce the image on the right. So going one step further, we work with them to create Gazebo plugins that interact with the shaders. So just have a couple of interesting examples to show here. So the one on the left is the wheel tracks plugin. So wheel tracks are important. So the operators would like to know where the robot's been to, so they want to see tracks being drawn. So what we did there was in the plugin, we sample positions of the wheels over time as the robot moves around the environment. And then we draw them on top of a single channel texture that you see on top here. And then that texture is dynamically updated and accessible by the shaders. And they use that to perturb and blend with the terrain normals to give the look and feel of tracks. So we have these tracks drawn while the robot was moving around the environment. And the next example there is on the right would be the camera exposure plugin. So on the polar regions of the moon, you have situations where often the camera points at the sun, and you want to test different camera exposure settings. So for simplicity, we expose a ROS topic, which takes a parameter, just the camera exposure setting, and then we pass that down to the shaders, and that affects the output accordingly. So as mentioned before, the sun, lighting is very important. So typically the sun is only a few degrees above the horizon, so you get a situation where the camera points or looks at the sun quite a bit. And then you get this strong glare, and we want to model these effects. So we added lens flares to Gazebo. It's basically a sensor plugin that you can attach to any of the cameras. We'll look for the first directional light in the world, and we'll put the effect there. So it's just a post-processing effect like the ones you see in games. It's not physically based. So what that means is basically you have an image, and then you just overlay the effect on top of it. But it works well it works with wide-angle cameras too. They're using wide-angle cameras for the hazard cameras. So you see on the bottom right there. We also do occlusion checking. So basically, we shoot out rays from the cameras towards the light sources, and we look at how many rays are occluded, and then we scale the effects accordingly to give illusion that is being occluded. And that's important because the rover will be driven into large craters. There are also distant terrains that will occlude the sun, so you don't want it to shine through the terrain. And also the last thing that we did was shadows. So in general, the quality of shadows in Gazebo was just of poor quality before. And it's something that we spent a little bit of time on at the end of the project. So when you have a situation where the camera direction is coincident with the direction, you get these warping effects on the camera shadows that maps that are being generated, and we get these jagged edges that you see on the middle image on the top. So what's even worse is that the algorithm we used to smooth the shadows wasn't good at preserving small features. So when you have shadows that's small, or for something that's long and thin, like the mask on top of the rover, previously it had a lot of cracks and made it look like it's disconnected. So that was bad. So we made several improvements. Basically, we changed the way, we tweaked the way we did shadow map generation. We increased the shadow texture resolution as well. And then we also changed the way we render and smooth the shadows, which is in general faster. And it does a much better job at preserving these small features, so you get this nice, sharp, crisp shadows that you see on the bottom. So to finish off, let me play a video. Oops. So I want to show you a video of the end result. So this is a scene rendered by Gazebo. This is a view taken from one of the stereo cameras mounted on top of the rover. So right now the rover is just being driven manually, and also the pinto is also controlled manually. So you see the terrains in these are DMs that are close by, and the distant one are just coarse meshes. You see on the top there's the lens flare effect that we place where the sun is, and robot is moving is kind of bumpy because of the high resolution DEMs. So here, what you see that's slowly coming into view, on the left you have the shadow spot. Here, you see the wheel tracks that are being drawn as the robot moves around the environment. All right. Oops, I don't want to share. Okay, so the last thing I want to show is that how we're close to end-to-end simulation of their operation. So, so the data we produced by Gazebo in simulation was published over ROS, and then over another bridge onto their software. So this is one of the tools they use by the members in the ground team to monitor robots. So for example, you have the image kept produced by Gazebo into their software on the top. You also have data of the pose of the robot in their traversity map. So we almost had end-to-end simulation working. And oops. And that's it. So I want to thank everyone involved. We want to thank the NASA Ames Intelligent Robotics Group. So we worked with a lot of these that you see here on these features, bug fixes. We think we were able to integrate them back to Gazebo 7. So a lot of these plugins, like the lens flare plugins, the height map, level detail plugins, they're all available and has been released already that you can readily use. Some parts are not available, like, for example, the high resolution DEM and their shaders. I know it's a very complicated process for them to get approved and released to the public, so that may take some time. But a lot of the improvements have been merged into Gazebo 7, which is the target version that they were using with ROSCon. And that's it. Thank you. So the question was, there's a lot of interest in using synthetic cameras, generating synthetic cameras for cars, for driving operations. And the stuff that we did here, are they available? So I want to say, in general, like we made several improvements to performance, shadows. Those are already integrated in Gazebo, but so a large part of the appearance comes from the shaders, but that's very application specific. It's used to capture the reflected properties of the lunar surface. So I don't think that will help for driving operations. But when I mentioned that we're working on the next version of our rendering engine, which is based on physically based rendering techniques. So hopefully that will help them.
How are you dealing with the physical simulation of regolith and moving through it?
So on the physics side, we only have the high resolution DEM. So that's basically all we have. So when we're doing all these tricks to do like have normal maps and also level details and all that. It's not affecting the physics. So physics, we preserve the high fidelity DEM files to simulate all the obstacles for physics.
So does that mean it's effectively moving over a solid surface, or is it more like sand?
It's more like solid surface.
Okay.
But with wheel slip model through a different plugin.
Okay.
Okay, we should stop there. Thank you.
Okay, thanks.